In previous videos, we have derived mathematical formulations for two important concepts: the mass balance equation, which governs how the concentration of a substance varies in time due to the variation of transport flux in space, and the expression for the total transport flux. When we combine these two equations, we obtain a general equation that governs how the concentration of a substance varies in time and space due to the reactions and transport. We call it the reaction-transport equation. We emphasize that this equation only describes the variation along one dimension. Specifically, we assume that the concentration of a component only changes along the x direction, while it is homogeneous in the y and z directions. A major objective in this course is to model processes that occur during early diagenesis in aquatic sediments. An important feature of aquatic sediments is that they are porous media. Additionally, processes during early diagenesis involve reactions between multiple components. In this video, we will explain how to incorporate porosity into the reaction-transport equation and what to do when formulating models that involve multiple components. Before we continue, we simplify the equation a little by assuming that the cross-sectional area A is independent of the distance along the model dimension. This assumption will be valid in all models that we are going to explore in this course. If the area is constant, it can be taken out of the spatial derivative and cancelled out with the area in the denominator. Thus, the simplified reaction-transport equation will have a form as shown in the orange box. We note that it is a second-order partial differential equation with four key terms: the rate of change of the concentration in time, the term due to diffusive transport, the term due to advective transport, and the net reaction term. The solution to this equation is a function of time and space. For example, it can be a function that describes how pore water concentrations of nutrients vary with depth in the sediment, or how concentrations of pollutants vary along an aquifer. An important feature of aquatic sediments is that they comprise two phases: the solid phase, containing mineral and organic matter particles, and the liquid phase, containing water and dissolved substances. The fraction of the bulk volume that belongs to the liquid phase is determined by a parameter called porosity, which is typically denoted as V. In contrast, the fraction of the bulk volume that belongs to the solid phase is determined as 1 minus the porosity. It is important to note that in systems we are going to model, porosity may change in space. For example, porosity decreases with depth in sediments due to compaction, as shown in the image on the left. However, the most important variation occurs at the sediment-water interface, where porosity rather abruptly changes from a value of 1 in the water column to a value lower than 1 in the sediment. As follows from the definition, porosity is a relative measure. Thus, in principle, it has no units. However, it is much better to consider porosity as a parameter with the following units: cubic meter of pore water per cubic meter of bulk. Consequently, the solid volume fraction, which is calculated as 1 minus porosity, is in the units of cubic meter of solid per cubic meter of bulk. We will see the benefit of this later when we formulate transport fluxes and process rates. There are multiple roles that porosity plays in the reaction-transport equation. One role is that it influences the rate of molecular diffusion. In bulk water, solutes diffuse at a rate that is determined by the molecular diffusion coefficient. However, In porous media, the rate of diffusion is effectively lower because the same distance in space is reached via a longer path length. This is because the molecules cannot diffuse through the solid particles, but must diffuse around them. This path length prolongation is summarized in a factor called tortuosity. In sediments, tortuosity can be approximated by an expression that depends on porosity. Therefore, when calculating the diffusive fluxes of solutes in sediments, we need to use the effective diffusion coefficient calculated as shown by the formula in red. We typically use the subscript Z when referring to the diffusion of solutes in the sediment, in contrast to the subscript mol, which corresponds to the molecular diffusion coefficient in free water. The second role of porosity is related to how we measure and report values of concentrations. Typically, we measure the concentration of a dissolved substance by first extracting the pore water and then quantifying the amount of the substance in the extracted pore water volume. In this video, we will denote this concentration as Cl, where the subscript L indicates that the concentration is per cubic meter of the liquid phase. Similarly, we measure the concentration of a solid substance by first removing the pore water to obtain a dry solid fraction of the sediment. Then we quantify the amount of the solid substance of interest and typically report it in moles per gram of the solid phase. This value can easily be converted to moles per cubic meter of solid by multiplying it with the density of the bulk solid phase. In this video, we will denote this concentration as Cs, where the subscript S indicates that the concentration is per cubic meter of the solid phase. The most important role of porosity is the influence on the reaction transport equation. On the one hand, the mass balance equation that we have discussed earlier is formulated for the concentration in the bulk, for which we use the subscript B to indicate that the value is in moles per cubic meter of bulk. However, transport fluxes of solutes are determined by the concentrations in the liquid phase. Specifically, the diffusive flux of a dissolved substance is driven by the gradient of the concentration in the liquid and not by the gradient of the bulk concentration, as illustrated in the diagram on the right. Similarly, the advective flux is determined by the product of the flow velocity of the liquid phase and the concentration in the liquid phase. Thus, if we do not correct for the porosity, the total flux is expressed per area of the liquid phase. Similarly, if a reaction occurs between solutes, the rate will be expressed per cubic meter of the liquid. We will discuss later what to do for reactions that involve both the dissolved and solid substances. To account for the effect of porosity in the mass balance equation, we must carefully consider the relationship between the concentration expressed per volume of the bulk and per volume of the liquid phase. These relationships follow directly from the definition of porosity and from a careful analysis of units. Specifically, to calculate the concentration in moles per cubic meter of bulk space, we need to multiply the solute concentration in the liquid phase with the porosity. Similarly, to calculate the flux per area of bulk space, we need to multiply the flux in the liquid phase with the porosity. And finally, to calculate the rate per cubic meter of the bulk space, we need to multiply the rate in the liquid phase with the porosity. We recommend that you pause the video now to verify and better digest this result. Based on these conversions, we can now rewrite the mass balance equation. We see that every term contains the porosity factor. Now we assume that porosity is independent of time, which is typically a valid assumption on timescales of processes that we are going to study in this course. Therefore, we can take the porosity out of the time derivative and divide with it the entire equation. We obtain a differential equation where all terms are expressed per volume of the liquid phase. Note that porosity is present in the numerator inside the spatial derivative and in the denominator outside of the spatial derivative. However, we cannot cancel it out because porosity generally varies in space. We recommend that you pause the video now to verify and better digest this result. Similar analysis can be performed for the solid substances. Specifically, we know that 1 minus porosity corresponds to the volume fraction of the solids in the bulk sediment. Therefore, we need to multiply the concentrations, fluxes, and rates of solids by 1 minus porosity to convert them from the units per volume or area of solid to the units per volume or area of the bulk. Based on this analysis, we can therefore write the reaction transport equation in the porous media as shown in the orange box. For dissolved substances, the factor F is equal to porosity. Concentration and the reaction rate are expressed per volume of the liquid phase, and the parameter dF corresponds to the diffusion coefficient in the sediment. The parameter Vf corresponds to the velocity of the liquid phase, such as the velocity of a pore water flow induced by pressure gradients. For solid substances, the factor F is equal to 1 minus porosity. The concentration and the reaction rate are expressed per volume of the solid phase, and the parameter dF corresponds to the mixing coefficient of the solid phase, such as the bioturbation mixing coefficient. The parameter Vf corresponds to the velocity of the solid phase, such as the rate of sediment accretion. Reaction transport modeling often involves multiple components. In this case, we need to solve a separate differential equation for each component. It can often happen that the component A reacts with the component B. In this case, the reaction terms for the component A and B are not independent of each other. As a result, the differential equations for the component A and B are coupled. A peculiar situation occurs when one of the components is a dissolved substance and the other one is a solid substance. We will explain now how to deal with this situation because it is often the source of errors in multi-component models. We will do this using an example involving aerobic degradation of particulate organic matter in a sandy sediment. We start with the stoichiometry of the reaction, which is shown on top. Then, we consider a possible rate expression for this process. A reasonable assumption is that the rate is first order with respect to organic matter, modulated by the availability of oxygen according to the Michaelis-Menten kinetics. Because particulate organic matter is part of the solid phase fraction of the sediment, it is expressed in moles per cubic meter of solid. In this example, we use moles of carbon. Given the rate expression, the rate is therefore in the units of moles of carbon per cubic meter of solid per second. Using this value without modification in the mass balance equation for the particulate organic matter, we obtain a correct formulation. We can verify this by checking the units, which are equal for both the left-hand side and the right-hand side of the equation. Now, we turn our attention to oxygen. Based on the stoichiometry of the chemical reaction, we would assume that oxygen is removed at the same rate as carbon. This would be true if both quantities were expressed in the same units. However, this is not the case. Because oxygen is a dissolved substance, its concentration is in moles per cubic meter of the liquid phase. Therefore, the left-hand side in the mass balance equation is per cubic meter of liquid, whereas the right-hand side is in per cubic meter of solid. This means that the mass balance equation is not yet correct. Because the rate is per cubic meter of solid, we must multiply it with 1 minus porosity and divide it by porosity, as shown in the orange box. Only then will we obtain the correct expression for the rate at which dissolved oxygen is removed. This can be again verified by carefully checking the units. We recommend that you pause the video now and really digest this result. We conclude that the mass balance equation that governs the distribution of substances in time and space along one dimension has a form as shown in the orange box. The equation accounts for the effects of reactions, transport, and porosity. To formulate this equation for a specific substance, one needs to distinguish whether the substance is dissolved or solid. If the substance is dissolved, the factor F is equal to porosity, and the concentrations and rates are expressed per cubic meter of liquid. If the substance is solid, the factor F is equal to 1 minus porosity, and the concentration and rates are expressed per cubic meter of solid. If the rate is formulated for a reaction that involves both the solid and dissolved substance, one needs to be extra careful to ensure that the units of the reaction rate is correct for each component. To convert between the rates expressed per volume of the liquid or solid phase, one needs to use one of the expressions at the bottom.